When things move, they tend to hit other things, then those things move too. When you pluck a string, it's shoving back the air molecules around it, and they push the air molecules around them, and so on and so forth. When these finally push some stuff in our ear, these send signals to the brain saying, "Hey, I'm getting pushed around here. Let this be sound." A sound wave travels in varying levels of compression. So as molecules travel farther away from the source, the energy is spread so far out that it no longer has the ability to push anymore, sort of like the ripples in a pond. The pitch of a sound wave has to do with the frequency, or the amount of space in between ripples on a pond. The higher the amount of waves, the higher the pitch of the sound is. Sound travels among all states of matter, solids, liquids, and gases. And because sound waves like pushing against particles, the speed of the wave depends on how closely packed the particles are. And because of that, sound travels faster inside a solid than it would travel inside a gas. As you can see here, this experiment will demonstrate how sound travels between a piece of string versus the air molecules around us.
Wait, what is this?
Sound travels in all directions, just as the ripples on a pond. So you could imagine sound waves moving approximately spherical, as shown here. You can use the formula power over 4 pi r squared to calculate the intensity of a sound wave. Increasing the radius decreases the intensity, since the energy is more spread out as the sound wave furthers away from the source. However, the intensity of a sound does not necessarily determine how loud it is. In the human ear, the sensation of loudness is logarithmic. So to find out how loud a sound is, you must take the log of the intensity and multiply it by 10. So as the musician plays his saxophone, the sound can be heard in all directions. The next thing I'd like to talk about is the Doppler effect, a phenomenon where the pitch of a perceived sound will change as it moves towards or away from the listener. When a sound moves, the source for each sound wave will be different, as there will be displacement between each one. So as you can see in this video game, you can hear the sound's pitch deepen as the penguin falls further and further away from the sound. Now, every object has its very own natural frequency. If an external force acts upon this object at this same frequency, they are said to be resonant with each other. As shown in this clip, the wind outside is causing this bridge to oscillate at its natural frequency, resulting in this waving movement. When a string vibrates, there is a fundamental frequency that relies on the length of the string and the speed of the waves on the string. We can find this by multiplying the harmonic number, which is the number of standing waves on the string, by the ratio of speed divided by 2 times the length of the string. I will demonstrate this by creating multiple sine waves following the pattern of a harmonic series. Individually, they sound very different, but if we play them all at the same time, they all match up to the same sounding pitch.
Thank you for watching.
A physics expert once said that in music, the mixture of harmonics that produces the characteristic sounds of an instrument is referred to as the spectrum of the sound. From the perspective of the listener, this spectrum results in sound quality, or timbre. A clarinet sounds different from a violin because of differences in timbre. Even when both instruments are sounding the same, at the same note and the same volume, the rich harmonics of most instruments provide a much fuller sound than that of a tuning fork.
Right. Yeah.
Oh! Did you see that?